When you play a game, your GPU isn't just drawing, it's orchestrating a massive multi stage factory line. Today, we peel back the silicon to see how a single pixel is born from raw math. Everything starts with your CPU. It doesn't send images, it sends instructions, a stream of vertex mathematical points in 3D space alongside texture and shaders packed into a buffer. This data arrives at the input assembler. It's here that raw numbers are organized into geometric primitives, points, lines, and most importantly, the universal language of graphics, the triangle. Now we enter the vertex shader. This is a massive parallel operation. Each point of our triangle is processed by a different CUDA code, calculating its final position on your specific screen. It's not just position. We are calculating lighting vectors and texture coordinates. We are transforming world space where the object lives into clipped space, what your camera actually sees. Next is primitive assembly and clipping. If a triangle is behind you or partially off screen, the GPU's fixed function hardware chops it up. It ensures we don't waste power on what isn't visible. Have a 3D math, but your monitor is a 2D grid of pixels. This bridge is called rasterization. The GPU tests every pixels to see if it's covered by our mathematical triangle. This isn't simple yes or no. The GPU uses barycentric coordinates to interpolate data across the surface. It's calculating exactly where inside the triangle each pixel sits. For every covered pixel, we generate a fragment. A fragment is a candidate pixel. It has a position, a depth, and it's waiting for the most complex part of the journey, the fragment shader. The fragment shader is where the visible magic happens. This is a program you wrote to determine color. It's calculating shadow reflections and sampling textures from the GPU memory. In 2026, we use PBR physically based rendering. We are simulating how light photons bounce off surfaces. Is it metal? Is it glass? The shader solves the physics for every single pixel. But there's a catch. We might have five triangles stacked on top of each other. Which one is on the top? The depth test or Z buffer compares the distance and discards the hidden fragments. This is happening across thousands of cores. On modern NVIDIA hardware, we use HyperQ and specialized schedulers to ensure the silicon is never idle for a single nanosecond. Finally, the fragments are blended. We handle transparency and anti-aliasing to smooth out those jagged edges. The result is written into the frame buffer in video RAM. The frame buffer is a giant map of colors, but it's not displayed yet. To prevent screen tearing, we use double buffering. While you see one frame, the next is already being built. The display controller reads the memory and sends a signal to your monitor. From a 3D vertex to a colored photon hitting your eye, the entire journey took less than 8 milliseconds. This is the journey from maths to pixels. If you enjoyed this bare metal deep dive, subscribe for more. Thanks for watching, and I'll see you in the next one.